So in our final week, we have Professor Rozenblyum, who will be speaking on miraculous duality.
All right, thanks very much. Already things are not so miraculous. That's all right. We'll make the best of it. I want to start off by I want to start off by talking about kind of Verdier duality or D modules. Maybe this is a review. Has this been discussed?
Yeah.
I see. So suppose, well, in any case, this I do want to discuss regardless. So suppose we have a quasi-compact scheme. Everything is always locally almost a finite type, or more generally, what's called a QCA stack. I know this notion came up last week, at least, maybe also in Curiel's talk. But anyway, so for now, just think scheme. Here's a kind of a categorical approach. To Verdier duality. D modules. Well, what you can do is the following. You can observe that given a sheet Q, given the D module, the X plain text, we can define F sub Q from D modules on X to itself. Namely, what we do is we consider our favorite correspondence, first projection, second projection, and we define this functor of a D module. D, well, you pull back the D module, you tensor it with Q, and you push forward with respect to the second projection. So it's like an integral kernel. If you think of D modules as solutions of differential equations, this is literally implementing an integral, and X is proper. This is literally implementing an integral kernel for the. This is like going to be the set of differential equations that the integrals transform of your function will satisfy. But anyway, so then what you can so what this does. So this gives a functor from D modules on X times X to, well, continuous. So both of this, so continuous here means preserving all colimits, functors of DG categories from D modules on X. D modules on X. So another way of saying it is that, so this is this kind of integral kernel construction, and we can take, I guess I didn't have to do this for X itself. I could have done it for X and Y. I don't know. Y. So this, oops, and this is in fact an equivalence. Is equivalent as functors from D modules on X to D modules on Y.
What are the assumptions of X cube?
What's that? Let's say they're schemes. Or QCA stacks is okay too. So, this should look strange. The reason this should look strange is because the left-hand side is completely symmetric with respect to x and y. The right-hand side is by no means symmetric. This is saying that there's some way to identify functors from d modules on x to d modules on y with functors in the other direction. What gives? So, you can try to take the adjoint, but that's not right, because the adjoint of one of these need not be of this form, need not be a co-limit preserving function. Well, there's always, so there might not be a left adjoint, there's always guaranteed to be a right adjoint, but the right adjoint might not preserve co-limits. So what gives? And the explanation for this is that this category, so it's F, so Y, this metric, in x and y. So the explanation is that, in fact, category of d modules on x is self-dual. So I think duality was discussed. So what it would mean to give us self-duality data. So first of all, we know. Let me just say a little bit about what this means. So first of all, we know under our assumptions, in either case, we know that this category of d modules is compactly generated. So compactly generated categories are always dualizable. The dual is compactly generated by the opposite of the category of compact objects. So it's dualizable. Dualizable is a property of that a DG category can have. That's a very nice property. Being self-dual is not a property. Being self-dual, you have to specify. You have to first. It's two things. One is it's the property of being dualizable, and two is it's giving an isomorphism between the category and the dual category.
Why is it dualizable?
Why is dualizable just a property? I mean, it's defined as there exists a dual.
There is some dual.
Yeah, that's the definition of dualizable. Okay. Now the uniqueness of dual, then that's a question you can ask, and it's unique. It's as unique as you might hope, reasonably. So now, how does this work? Is, well, we need to let's give the duality data. Well, what do we need to do? We need to give a functor from vector back to d modules on x. D modules on x. And then down to vector. Yeah? So the key point is that, well, under our assumptions, in fact, much more generally so, d modules on x tensor d modules on y is equivalent to d modules on x times y. Of the unit, co-unit. So, and notice objects here are the same thing as kind of functors in either direction. And now the kind of this is called Verdier duality, by the way. So this is a kind of an abstract formulation of Verdier duality. Explain how this gives you usual Verdier duality. So the unit, co-unit are both given by in the kernel of delta lower star of omega x, where delta, of course, is the diagonal.
We don't think the kernel doesn't determine the co-unit a priori, right? Don't you have to specify? Seems like you're kind of implicitly using self-duality.
No, I mean, I'm using this identification. just read the kernel in the other direction.
Okay, I see.
That's why
I see.
that's why I started off talking about this.
Right.
And this is explained. There are various ways of thinking about it. This is explained by the fact that the way the theory of D-modules is set up. D-modules you can think of as a functor, as a symmetric monoidal functor from correspondences of schemes to categories. And in correspondences, everything is self-dual, and you just and this is the thing that transfers over that self-duality. So I don't want to dwell on this point because, well, it's a very important one, sorts of reasons, but it's not going to be the main thrust of what I want to talk about. So anyway, so I mean, one way or another, it's very easy to check that well, I've defined two functors like this using this isomorphism. Well, there's always a functor here, which is box product. Assertion is that this is an isomorphism. So I guess there's always the co-unit is always defined. In order to define the unit, I use the inverse of this. But anyway, and it's, well, one way or another, it's easy to check that this defines the duality data. And so this gives so in particular, the self-duality, so recall that D modules on X is compactly generated. What this means is that a self-duality is equivalent to an equivalence of categories between the category of the compact objects. Was that the notation, or and its opposite. And this really is Verdier duality. This is usual Verdier duality. This is Verdier duality for D modules. Hey. The way I want to think about Verdier duality is this self-duality of the category of D. Okay. Any questions? All right. So now, you could have asked, well, what's special about this guy? Well, I told you one thing that was special, which is that if you think about, this functor formalism about correspondences and upper shriek and lower star, then this is then this is the thing that comes from correspondences. But we made in some sense we made an arbitrary choice. We were thinking, for instance, about not D modules, but other kinds of sheaves. We could have taken our other two functors, which is upper star and lower shriek. And so we can also consider the lower shriek of the constant D module. So this too defines a self-duality. Duality. Well, in fact, here, so let's really assume that X is a scheme. Then, well, delta lower shriek is the same thing as delta lower star. So that's not very interesting. In the case of a stack, that's no longer true. But although notice that in the case of our QCA stack, delta, this guy is still defined. The reason that this is still defined is because the constant sheaf is holonomic. So for holonomic D modules, you always have the shriek pushover. But anyway, so for schemes, say schemes. In general, this is not true for stacks. So this is the same as this guy minus 2D. D is the dimension of X. So of course, well, it's just the same bunker. Everything's the same up to a shape, so it's fine. It also
It's assuming X is smooth though, right?
oh, this is assuming that X is smooth. Yes. Yes, smooth.
Is it still a perfect area?
Oh,
Just those schemes?
no, it is not. It's oh, thank you. Great. But the point is, I mean, what is the meaning? So you can ask, well, what is how to think about this guy? So as it turns out, regardless of whether, so maybe let me just give a definition. So X, so this is kind of more interesting in the case of stacks. So let me say X is a QCA stack. It's miraculous if this guy gives defines a self-duality, gives a self-duality. So this is kind of a different duality than Verdier dualities. Potentially, you can have kind of another one. So, but I want to. Well, why are we talking about this in this context? This kind of seems like a weird idea. But the idea will be this: that we want to apply this to the stack BunG. So BunG, as we know, is not quasi-compact, and what that means, a consequence of this is that you can do this analogous thing, and try to see if you get a duality data this way, and the answer is no. That's false. It is not Verdier duality does not work for BunG in the way that you might hope. Just false. Unless G is a torus, then it's okay. Lots of things are okay then. But on the other hand, for various reasons, you want it to be self-dual. If nothing else is because that's predicted by the geometrical invariance conjecture. Because the geometrical invariance conjecture says that BunG is something to do with local systems, and that category is self-dual by our Serre duality. So, and what we'll see is that this version of the self-duality actually will work for BunG. Have some kind of nice, interesting consequences. Okay, so that's sort of where we're going. But first, I want to talk about allegorical approach. To this, like, there's nothing specific about the category of D modules or or anything. It's just something about compactly. It's like this thing makes sense in some sense. Some version of this object makes sense for any compactly generated DG category. So the abstract formulation is like this. The compactly generated DG category. So in particular, it is dualizable. I'm going to make use of compact generation. Probably this can be generalized somewhat. I'm going to need. So here is kind of a weird observation. is there's a natural functor from the opposite category to the dual category. Remember, the dual category is the nth category of the compact object opposite. So you're sort of this is the pro category of the compact objects opposite, and the idea is that you have inside here the opposite compact objects. So that naturally maps into here as the compact objects. And this guy is what's called the right conextension. So let me say the word and I'll explicate what this means. This is what's called the right conextension. I want to give this functor a name. So let me. Abstractly, and then I'll try to specialize this up. So explicitly, X is co-limit of xi. This is in C. Let me give this functor a name. Let's call it psi. Pseudo. Then psi of x, you just formally define as the limit of the xi's. So I hope it makes sense because so xi objects. So there's some transition methods. So this is a diagram in the compact objects. You take the opposite. That's a diagram indexed by the opposite thing in the opposite of the compact objects, and you take its limit. So maybe. Yes, sorry. Let me denote it by x cap. Let me call it check. Or something that's some kind of duality. This functor will be called check. So, so in other words, we're writing this. It's characterized by the following property: that in this check category of x check from y next check for y. This is equal to, so for y, if you take an arbitrary object, it's check, then from it to this object, this is the same. Let's take it as a compact object. So that's enough to say. Let's see. Y. C compact. So mapping a compact object into it is the same as mapping in C from X to now Y. Y thought of as an object. I hope it's clear what this means. Okay. So this is a so we have such a thing. But we have such a weird construction, which maps the opposite category into the dual category. On compact objects, this is just compact objects, this is kind of doing nothing, and you kind of extend by limits. That's the idea. Okay, so now, well, what's the so now we can define. So now let me have the unit. So this is the image of the unit. So maybe let me remind you, I guess I should have reminded you, that this category, C tensor C check, is identified with endofunctors of C. Hope it's clear. This is how duality works.
Contiguous, right?
Continuous, yeah. Let me write it there. C, and the unit is the thing that corresponds to the identity functor. And now, define the pseudo identity of C. This is just this check construction applied to you as an object of C tensor C check. So this is an element of C tensor C check, which we can again identify as C tensor C check. I don't know, C check tensor C. So this is pseudo identity. So in the case, so the first assertion is that in the case of a QCA stack, it exactly is given by this kernel. Exercise that I'm not going to do. So for is U modulus on X, QCA stack, pseudo identity. See, this is given by. So again, this is a functor from it to itself, so that's given by an integral kernel, and the integral kernel it's given by is this one. A kernel is so that's kind of the abstract way of talking about. So that will be kind of a convenient abstract way of talking about this guy. And so let me just give you an example to get your hands on what happens. I think a useful example to keep in mind. Example. If C is A mod for an associative algebra A, e.g. algebra A, then of course Justin explained that in this case, the dual category is the category of modules over the opposite algebra. Yes.
I don't think it actually came up.
Oh boy, okay. Well, so this you can think of as left modules, this is right modules. And so, well, let me just, so the, well, so, okay, let me sketch a proof of this for you. That will be relevant anyway. So I have to give a unit and a co-unit. So let me say what those are. But this is identified with A tensor A up. I don't need to ask. I know Justin explained that. That's essentially for us the defining feature of the Lurie tensor product. But that's not the definition, but the definition is rigged so that this will happen. And well, so these are bimodules. I'm supposed to give you a bimodule, and the relevant bimodule is the diagonal module. Okay. There's a particular element here, which is the diagonal bimodule, and this is what implements. Sorry, so that's this functor. Now I have to say what this functor is. I don't get to use integral kernels because there's no geometry. So this functor just sends k to back to A. And this functor sends M to the tensor product of M with A. So this is the anyway, this is if you like think about dualizable DG categories, this is an important example. This is always the first example to consider. Let me call this and so in this case, pseudo identity K mod. So that's a bimodule. This is identified. So that's kind of internal HOM in bimodules. From the diagonal bimodule to this. So this is kind of the dual of the diagonal bimodule. In the case that this is in cases where this makes sense, this is closely related to the Sayre function. So I don't want to get into that, but it's good to mention. I think this is for this, at least in Ginsburg's notes on non-commutative geometry, I think this is called the Auslander-Reiten functor. Okay, so that sort of tells you some idea. Like for instance, if this is like for instance, if A is smooth and proper, this will be perfect, and also I guess just if it's smooth, then this will be perfect as an A tensor A out module, and so its dual will also be perfect. A tensor A out module, something nice happens in that situation. Maybe one thing to say is that one way of thinking about this functor. There's another way of thinking about this functor is that this is certain kind of functors out of the opposite category. Sorry, out of C, just by the Uneda embedding. This maps into this embeds fully faithfully into functors out of C, in functors from C into vectors, not necessarily continuous. This, by definition, almost by definition, is the same as continuous functor C into vector. And if you have a compactly generated category and a functor somewhere, then you can always kind of universally make it a co-limit preserving functor. Namely, just restrict to compact objects, and then just index extend from that. And this is another explanation for what this check functor is doing. All right. should have said some QCA stats miraculous or not. Maybe I'll say without, just to advertise, a prototypical example. Miraculous stat. It's A on mod GM, where the GM acts the same on every factor. It's just acts by scale. So this is a nice it's a nice thing to work out. If you want to look at why, so the paper to look at is Dennis Gatesgory's paper on kernels and functors given by kernels, adjunctions, and duality. Okay. So for us, our goal is going to be to show that BunG is a miraculous stack. But so far it doesn't actually it doesn't quite make sense because BunG is not quasi-compact. Oh. G. And G modules BunG is not self-dual in an obvious way. Standard way. In a standard way. Okay. So all right. That we're supposed to take a break. What's that?
In 5 to 10 minutes.
Okay, great. I want to so for BunG, for stacks like BunG, there's another category you can define. So recall, you have the following description: D modules and BunG. So let you see post that open substacks. You BunG at the intersection. You with every connected component G is quasi-compact. So yeah, so this issue of quasi-compactness, there's no problem with taking infinite disjoint units. That works just fine. It's like what the problem is, things like BunG for like SLN, where it's connected and connected and not quasi-compact. So this is the thing. So we have the D modules on BunG. This isomorphic to the inverse limit over this category of D modules on U, where the functors are just pullback, the D module pullback. J upper star equals J upper shrink. Because it's an open embedding. But we can also define, but now we can define on a co, the co category of the D module. This thing, co D module, I don't know. To be now the direct limit. So there's an op here. D modules of U. So just this is along just J lower star, so along push mark. So that's the functor. So a priori, these two categories don't really have anything to do with each other. But what we know about BunG is that BunG is truncated. BunG, yeah. The word. What's that? Well, for BunG, so this makes sense for any stack. This op QC has
I think it's truncatable, actually.
truncatable.
Truncative is like.
Oh, yeah,
Be if like
Okay.
close to that.
Yes. So this category, you see, has a cofinal. So it has a cofinal subposet. Every, let me say, lies inside U prime by G, where U prime is co-truncated. So the property that BunG has is that every quasi-compact open sits inside a co-truncative quasi-compact open. And this line inside, that's a cofinality. So in other words, we can take the co-limit and take co-limit over co-truncative. Open subsets. And now for these, the J lower star preserves co-limits, essentially by definition.
Preserves compact object.
Sorry, preserves compact objects. Please preserves co-limits. Preserves compact objects. So we can rewrite this as a diagram of categories where the transition functors preserve compact objects, like generated. And what this means is that this guy is compactly generated. Follows that. Control is compactly generated. Now I should have said. So we have this self-duality. There's a yoga to be played, to be done with self-duality, which is that if you have a functor, there's a corresponding dual functor that goes between the dual categories. But if you've identified the dual categories with the original categories, this is a way. I guess that's the answer to my original puzzle about how you make functors from d modules on x to d modules on y symmetric with respect to x and y. If you have a functor, you can take its dual, and because using the self-duality, you can interpret it as the same as also a functor between d module categories in the opposite direction. And so the point is that given a map space maps. U to V and R3 is dual to F dollar star. In particular, in these transition maps, yeah, so we know that this is dualizable, and so the dual you can calculate by taking the dual of each thing and taking the limit. And so now the dual, these d mod on U is self-dual, and the dual of the transition functors are the transition functors here. And so taking the limit, this means that homologically, dual gets identified with d modules on G. So notice, like, let's compare the situation with what would happen if like instead of BunG we took something quasi-compact. Well, then this category would have a terminal object, which is just X itself, and then these would be kind of canonically identified, and this identification would correspond to the usual Verdier duality. So the thing that's analogous to Verdier duality, the version of Verdier duality that you have for BunG, is not a self-duality of the category, but that the dual of BunG is this kind of co-category. What we'll see, in fact, is that we'll be able to identify that, and that's what miraculous duality will do. Okay, so that's all right. Welcome back. So I want to. So this kind of statement is true that we arrived at for any truncative stack. What will be miraculous about BunG is that this will be true without this guy. And so how do we describe this? What's the relationship to the pseudo identity? Is the following. So let's contemplate what functors are from this co-category. D module category. D modules. G. Both are dualizable. So continuous functors between from C to D is the same thing as the tensor product of C check tensor D. So this is category of functors is this tensor product here. But now we have this identification. Let's apply it. So this is just given by D modules on BunG, tensor D modules on Y. But now BunG, you know, you don't. So it is true still for BunG that that the natural functor from the tensor product of D modules on BunG with itself to D modules on the product and the Cartesian product is an isomorphic. This guy is isomorphic to D modules on BunG. So what we arrive at is that, well, before in the quasi-compact case, we had that the D modules on the product were kernels for functors between D modules on one and D modules on the other. Here, the symmetry is broken. Now a kernel on BunG, a D module on BunG defines a functor not from D modules on BunG to D modules on BunG, but from the co-category of D modules on BunG to D modules on BunG. So, well, which is maybe good news for us, because we want to our goal is to identify the two. So we want to for initially what we want to do is we want to write down a function, at the very least we want to write down a function. So to write down a functor, we need to write down a kernel, and there will be two that are relevant. Sort of this. So there are kind of two versions of pseudo identity. Fine. Pseudo identity star G to be the kernel given by the lower star of so the usual thing G and pseudo identity on G delta lower sure. By the way, notice that because BunG is not separated, lower star and lower shriek are different functions of the constant G. So BunG is smooth, so this is the same thing as the difference between the constant sheaf and the dualizing sheaf is just given by a shift, twice the dimension. So there are these two. So all right. Now I'm going to. This is going to be the stage in the talk where I'm going to abuse notation and use objects here with such functors. So let me state a fact. So the pseudo identity functor. Otherwise, I just don't have enough names. Things. So the functor induced by pseudo identity from this star. So this is what would if this was so this is what would correspond to the usual Verdier duality, if that were a good functor. G. Oh, okay. So if there was no co and BunG was quasi-compact, this would be the kind of this would be the identity function. Is not an equivalence. For G not a torus. As long as your group is, as long as you have a positive semisimple rank, then this is not an equivalence. You can write that like refer you to this paper, so where there's a more or less an explicit object here that's in the kernel of this.
Fine. Would like the constant sheaf be in the kernel? Seems like the kind of thing that would come from.
Yeah, it was something like that. Yeah. But so the theorem duality which is that this great pseudo identity functor is an equivalence. So the analog of this kind of weird, so the analog of Verdio duality does not work, but the analog of this weird duality does work. So that's the way in which the category of D modules on BunG is self-dual. So how to prove such a theorem? So this is by no means formal. This is a pretty deep statement about the moduli stack of G modules. So the general strategy the general strategy is well, which is I think how you prove most non-trivial or many non-trivial things about BunG, is by induction on the semi-simple rank. Yeah.
Is it not true for general truncatable stack?
No.
There are some examples.
I mean, there are examples of QCA stacks where this fails. So an example where this fails is take I think A2 minus the origin with GM acting hyperbolically, and take that quotient stack. If I remember right, this fails to be miraculous. So yeah, no, this is really something very special about BunG.
You said probably also for singular schemes too.
Yeah, that's right.
Yeah,
Yeah,
I'm curious.
let me answer that question later. This requires more thought than I'm capable of at the board in real time. So by induction of semi-simple rank. So the idea is we have these functors of Eisenstein series of constants that were introduced last week, and so that this allows you to go from D modules on on levies of parabolics to D modules on BunG, and so that gives you some control over some objects, but that doesn't give you everything. And the idea is that the thing that somehow makes BunG really special is that if you take the things, I'll say it more precisely in a second. If you take the things that are not, in the category that are orthogonal to the category generated by things that you get from Eisenstein series, then those are supported on compact systems. And so for that, we kind of already know. So I think this is kind of the main reason that BunG behaves as if it were kind of quasi-compact, is that you can kind of induct down to get to BunT, which is just a disjoint union of quasi-compact things. And then for other things, as long as things work well with Eisenstein series functors, the kind of the complement to what you get from Eisenstein series is compactly supported.
We can ask a slightly better question.
Yeah.
What if your stack is truncatable by miraculous co-truncated substacks? Will the union be miraculous? I just want to understand how non-formal this statement is.
No, this is very normal.
Like, what does it really use about the BunG?
I'll tell you, it uses a lot. And it uses, anyway, anyway, it's very normal.
So I guess if the answer to your question was positive, it would be the formal proof of this, and the answer is probably no for that reason. But
Well,
No, but then.
oh, no, I don't know. So I don't know offhand the answer. I have to think. I mean, what's not at all clear to me is how to prove that the things that make up BunG,
Are
the case are themselves miraculous. That doesn't seem to be any easier than like you.
Well,
It doesn't
yeah.
seem like you've made the problem any easier.
Yeah.
Anyway, I'm not sure offhand what the answer to your question is. Again, that requires more thought than I'm capable of. But even if yes, it's not clear how that would happen. So to remind you. We have E parabolic subgroup. U so we have this beautiful correspondence. I'm doing this quickly because this was talked about just last week. So and we have the constant term star functor, which is defined as Q lower star Q upper shriek. So a non-trivial fact that was discussed last week is that this admits.
I think P and Q are swamped there. Oops. P and Q are swamped.
All right, I'm just looking at my notes. I wanted it to correspond.
I think those are the standard letters. So.
Yeah. Yes. And yes. I mean, yes. So this admits a left adjoint. A non-trivial fact. Which is, of course, you can write like this. But the non-trivial fact is that this is defined. That there exists. Okay. So you can also sum up over all the mu's. Everything's great. So let me remind you of the theorem from last week is that mu is the right adjoint. Is the right adjoint. Over star mu minus for the opposite parabolic.
Should the I shriek or
What's that?
you just didn't define as stars?
Oh, sorry. Whoops. Said it correctly, but I forgot to define ice star. No, it should not be ice ring. Fine. So the star functors are the ones that are always defined. And the theorem from last week is ice star mu is the right adjoint. So the way this is set up is that stars are right adjoints. Freaks. Sorry, there's going to be a lot of these functors. It's hard to keep track. So the stars are right adjoints. The shrieks are left adjoints. Is how it's set up. The stars are tautologically defined. The shrieks exist for interesting reasons. This is the right adjoint. A constant on the star in mu, but for the opposite parabolic. i.e. equivalently, we have but this functor exists. I hope it's clear what this would mean. Just swap the shrieks and stars, and it's isomorphic to the same constant term functor for the opposite parabolic. This is another way of saying what this means. Okay, so that's just so in the same way, we can define. Sorry, now it's just lots of definitions. For a second, but time, okay. I'll try to do at least one thing that's not just giving definitions and statements. Sorry, it's sorry,
What goes in this blank?
blank.
CT. Where's it minus? Oh, right.
That's that's not blank. That's minus.
Right.
Minus means for the opposite parabolic. Anyway, there's some structure theory of reductive groups. So opposite parabolics have the same levy. Yeah, I don't. The first thing you need to know for this to even make sense. So well, we can do the same thing. Well, but now we can see. We can also define similar functors. So there's like lots of functors, right? Bad news is we're going to need some more functors, which is on the D module co-categories. So I mean, look, we're trying to compare. What is it that we're trying to do? We're trying to compare. We're trying to prove that functor is an equivalence. Well, the idea is we'll prove this for M. For T this is tautologically true. Because the co-category, the way things are defined, the co-category is the same as the category of D modules. And Verdier duality works for disjoint unions, infinite disjoint unions of quasi-compact things. And then we're going to say that for things that you get out of, and then what we're going to need is a compatibility of the pseudo-identity functor with Eisenstein series. And that's going to tell us that if, and that's maybe the most interesting thing. So that's the thing that I want to get to explaining is the compatibility of the pseudo-identity functor with Eisenstein series on both sides. So we need Eisenstein series for the regular D modules, and we need Eisenstein series for co-D modules. So, very quickly, define O star mu. This is, you take constant term mu star, and you take the dual functor. So the good news is that we can define, like, how do we define functors on the co-category? Well, we just use the fact that it's the dual. So we can take duals of things, and that naturally lands us in the O star. This is defined as, surprisingly, this guy, and there's two more. So there's constant term mu O question mark. You can see a creativity of notation. This is similarly I's mu O question mark to be the dual of the Schrey constant. Okay, importantly, formally from that theorem, so this kind of second adjointness type theorem tells you the following. that this constant term mu of question mark, this is isomorphic to let me the junction where the left adjoint O star and the right adjoint is Eisenstein O star with mu inverse. Right. So so these are identified for opposite parabolics. Okay, sorry, that's just formal consequence of what we said. So here's so now let me define. Apologize for all the definitions. So we can define the hospital category. So this is the category that's not seen by any of the Eisenstein series. So this is the full subcategory. Defined as the intersection. The kernels of constant term star. So these are for all proper. Of course, it's not interesting to take the whole pair. B itself is a parabola. Of course, that's not interesting. So this is the full subcategory where the constant term star vanishes for every proper parabolic. All right. Right. Equivalently, we can do the following. We can define kind of the Eisenstein subcategory. G, so this is generated by full subcategory. Generated by the Schrick-Eisenstein series. So then the hospital ones.
You mean span?
What's that?
Span or generated?
I don't know. I don't know what's the difference. What's the difference?
Well, generated, maybe you want to add something.
Well, no. So yeah. So what I mean is it's a full subcategory that you get from these and freely adjoin all, and just allow all arbitrary colimits. They're generated under colimits, if you like. Is the right orthogonal? So in other words, it's characterized by that something is in here if for every object here comes from the object here to this fixed object is 0. So this Eisenstein category. So the point is we're going to break. So this way we break up D modules on BunG into two parts, the hospital part and the Eisenstein part. And we're going to kind of prove this theorem kind of separately on each part. Wow, we are not going to do that. That's what K-square does.
You want to show that this hospital and the Eisenstein category is both miraculous?
Nope.
No.
No, I'm going to show that. I'll say exactly what. I mean, we have a functor, so we can restrict it. So first of all, it restricts it. Well, anyway, the game will be to see how the pseudo identity functor interacts with Eisenstein series. Particularly, it'll tell you what it does with. So I don't think I will get to say this, but also part of the game is the other pseudo-identity functor is relevant. Well, it's also important to know how that one interacts with Eisenstein series. It's going to be kind of the interplay of how both of them interact with Eisenstein series. I'll briefly comment, but I want to get to kind of, in some sense, one of the main things, which is the strange functional equation for Eisenstein series, which is which is how Eisenstein series interacts with this pseudo-identity. So, okay, so similarly, we have the same thing for the co-category. So this is generated by essential image. Importantly, I'm always setting this up, so it's generated by the essential image of the left adjoint, the version of the Eisenstein series that has a constant term, which is a right adjoint. And the hospital one. Hospital. Is the right orthogonal. This one. Eisenstein, sorry about that. And equivalently, this is the intersection of kernels. Of the constant term for question mark, because that's the right adjoint to this thing. Okay. Good. Okay, so this is what we have to work with. And so first of all, let me say the relevant statements about hospital things. I think I'm not going to prove. I definitely don't have time to prove anything about hospital things. I was going to say something about the proof, but theorem. And this is kind of before that, should just explain why. So the really key fact about all of this is the following. Position, let me say theorem. Is that there exists some quasi-compact open in something that I guess something that intersects every connected component, the quasi-compact open, such that for any hospital sheaf, such that any hospital D module kind of lives on this quasi-compact open. For any okay, so this is kind of the key thing that makes all of this work. The maps. Isomorphisms. It's like a version of cleanness too. So these are like cleanly extended in some sense. Well, I don't know, these are not reversed, anyway.
It's kind of, I'm just sorry, it's kind of a vague question, but it's sort of hard to imagine how you could have something that was clean without it being sort of regular. I guess that's not true. I'm just thinking of like usually it's
No,
like
no, it's a
regular, but
stacky phenomenon.
it's the stacking.
I mean, the reason that you're not. Anyway, there,
I guess it doesn't have to be irregular, I guess, because you can also have something like the multiplicative connection on GM extends cleanly over the
Right.
origin, so yeah.
yeah, but I mean, but also, all these things are like it's pretty important that we're like, a lot of these have to do with stacking phenomena. But anyway, yeah, so somehow this fact, this is the fact that makes everything go. And so, well, so the point is, this, that every smooth stack, it's a little bit like what Ariel was suggesting. I mean, every smooth stack, well, what one shows is that essentially by comparing, so you prove two statements here, that because there's this quasi-compact thing, that because of this a similar statement holds for this code. So this guy's a little bit more subtle to describe, but there's a similar statement. Well, half of it anyway. That's true. And so the point is, both are sort of, the way you should think of it is that both are sort of compactly supported. And so for those, the kind of naive pseudo-identity should be giving you usual Verdier duality. And well, then in this case, one can, in a relatively straightforward way, compare this on this quasi-compact guy, the naive. It turns out that the Verdier duality on this guy, compared with the Schrick pseudo-identity functor, differ by a shift. The shift is a little bit funny. It's like minus twice the dimension of G minus the dimension of the center. But I don't think I have time to explain that. A little bit, anyway, take us away from what I actually want to do. So that's the. So the statements, so the theorem is that this pseudo-identity G of the classical category this actually lies in the classical category. I don't know. Let me just say it uses an equivalence. Show is that this induces an equivalence between on G constant and the modules in BunG constant. This sort of anyway, sorry. This is not a formal statement, but maybe a believable one from this kind of description. There's other non-formal. That's not the only non-formal input to it, but
She said pseudo-identity Schrick and pseudo-identity star agree up to a shift there.
yeah.
And that's
Also,
what's like the mechanism for comparing those? Can you say use some special property of UG or?
oh no, it's not about UG. So what's always true is that there's like on all of BunG, there's a comparison between pseudo-identity shriek and pseudo-identity star shifted by appropriate with an appropriate shape. So that's something about BunG, and then the assertion is when restricted to UG, then that becomes a nice. And moreover, so pushing this a little bit further, we just state the so for any so the functor, let me just so pushing this quasi-identity a little bit. Identity, the key assertion of G. See my notation, opposite of that in the paper. These are swapped. That'll cause. So this induces isomorphism. Oh. Prime. G. G. This looks like a fully faithfulness statement, but so F is arbitrary, but F prime has to be custom. So this is ultimately what one needs to arrive at is this statement about cuspidal demodules. Okay, so let's take that as input. And let me try to at least give some sense of the remainder of the other thing in that mention is strange functional equation how that plays into it. So the remainder is to kind of analyze what happens. But again, this is just by essentially reducing one way or another. You somehow argue that you can reduce to a quasi-compact substack and deduce from that. Anyway, it's not formal, but it's that flavor argument. So let me focus on things that don't live on really don't live on quasi-compact parts, which is the isomers. Okay. So the key theorem is the following. So yeah, so this takes care of the cuspidal part, and now we want to understand the Eisenstein series. So the theorem, strange functional equation, says the following. So it's about the way that the Eisenstein series functor interacts with the pseudo-identity. So you start with a demodulin in the co-category of BunM. You apply pseudo-identity, you get an actual demodule. You apply an Eisenstein trig functor, and this is the same as doing it in the other order. But now, so you do the Eisenstein in the co-category for star. So that's good. That's the thing that's also a left adjoint. But you do it for the opposite parabolic. The fact that there's an opposite parabolic involved should tell you that it's something non-obvious, non-formal is going on. But where the opposite parabolic is going to come from is from the theorem that was proven last time, explained last time. So let me actually give a proof of this statement. Both are functors P and so are given by a kernels U in D modules. We're going to compute what the kernel is. The way you get rid of the co-categories is that you see that both of these are just D modules on the product, no co. So it's a statement that there's an isomorphism between two particular D modules. So that's what we're going to build. So we have to understand what the D modules are. I think that's a nice exercise to do, and so I want to explain how that works. So how does it work? Well, it's a composite. So let's look at the left-hand side. Well, first of all, how does first of all, so pseudo-identity so by definition, we know what the kernel of pseudo-identity is. That's just delta lower shriek of the constant sheaf. That's the definition of pseudo-identity. And now, if we want to compose that with ice lower shriek, we just apply ice lower shriek to one of the factors, so like the second factor. So the kernel by definition of pseudo-identity, shriek kernel for no, it's given by what? Well, I's shriek box tensor identity on M applied to the on M, right? So this is a functor from BunM times BunM from D modules on BunM to ID. So this is a functor from D modules on BunM, tensor D modules on BunM, to D modules on BunG, tensor D modules on BunM. And that's well, I swapped the factors, like no matter. So this is what we want to do. But now, what is the point? So the functor, this functor, so we have to understand this functor. So it's left adjoint. So this is a little bit complicated, right? Because of the shriek. So we don't quite know. So if it was star, then it would be easy. Then it's easy to write kernels for the star functors. It's not easy to write kernels for the shriek functors. But the point is, this is left adjoint to this guy, constant term star tensor, the same identity. And this, well, this is just id tensor Q lower star composed with, sorry, id times, or id. I can write this geometrically. Right, id times P upper shrink. So in other words, we can interpret this. Yeah, so this is that's the left adjoint of this. So sorry, it's the that's the right adjoint of this. So now, so the point is we can interpret it. So therefore, is the Eisenstein series for m times g with respect to the parabolic parabolic m times p in m times g, right? Just think of m times, just replace your group, just take m times g as a perfectly fine reductive group. It has a parabola called m times p. And this thing is that, what we see is that this thing is just a this guy is just a Schrick Eisenstein series for that. And therefore, so it is given by P over Schrick now we know this makes sense. So we didn't know this made sense before, but now we do, based on polynomial things. So now we're going to
This cross, that's the product between.
no, this is just these are just maps.
No, but
This-
between in the brackets. Position.
Composition product. Okay, great. So now we can now we can compute what this is. So well, let me draw the diagram. This is the graph of Q. G. This is the inclusion of the id times P. This is id times Q. This delta. Q. So base change. This is pullback. Base change gives that this guy id times P lower 3 opposed with id times Q for star composed with delta lower 3. Okay. Now, so I hope we agree. This is what we want to compute. That this is the same as U times P opposed with delta lower 3. Okay. So in other words, this is the same as if you take the so what is this guy? So what is the kernel at the end of the day? We're saying that you have a map from BunP to BunM times BunG. And you just push forward along this map the constant G. And part of the yoga here tells you that this is well defined. That this object exists. So this. So we want to identify the other one with this. Okay, now I'm really running out of time. I think I'll just say something about this and finish. So we want to identify the other one. So this was the easier one. My apologies. But the other one is no, it's not more work. It's just there's one other idea that I want to point out. So for the other one, we want to show that it's the same kernel. How do we do that? Go now. Now, what is the functor? So the functor kernel for identity G closed with Eisenstein followed R minus. Okay. So now it seems like we're stuck. In the there we had a good idea, which is that, well, we know by definition what the kernel is for pseudo identity, and then we just started from that. Here we don't have anything to start with. So the idea is this. The idea is that to instead consider the dual of this one. The point is that if you read the kernel backwards, that gives you the dual function. So the functor and the dual and its dual correspond to the same kernel. The dual is given by the same kernel. And you swap the factors. So I should have said that also for the same reason. You take the dual, this is itself. It's not true. You're asking you might ask why how did I get that? Like so I'm supposed to read it backwards. And reading it backwards in this case, because it's a map from D modules on G to D modules on BunG, I'm supposed to swap the two factors. But by definition, it's invariant with respect. It lives on the diagonal. So it's invariant because it's invariant with respect to swapping the two factors. So what happens is that this dual also dual switches composition, that becomes in the other order. So this becomes constant term. Oh boy. This becomes, well, whatever the dual is. Dual.
Oh, it's constant term star.
Dual is,
That's what you read earlier.
oh yes.
Co-star is dual to star, and co-shriek is dual to. Sorry,
Oh,
co-question
yeah,
is dual to shriek.
So yeah, so this is constant term star minus. Thank you, composed with energy, yeah. Energy. And now we're in good shape, because now we can play the same game and get the kernel. So again. So the CT minus, so well. So again, this is. So the CT, well, if I fix a mu. Sorry, there's a subtlety that we have to do this one mu at a time. So this is the left adjoint. This guy. And so the point is that this guy, if I put in a mu, whoops. So the upshot is that the kernel define this constant term star box tensor, the identity applied to 3 A. Whoops. Dual, because I'm describing the dual factor. So this ET mu minus star is left adjoint. So let me just say, so it's the same argument as before. Goes just observing what its adjoint is, that this guy, if I fix a mu, it is the Schritt constant term functor. Or E times G inside G times A. And so
Freaker start.
whoops. Thank you. So we have here is a maneuver that somewhere something happens. Here is where it happens. Yeah. This is it. And so now we study this guy because the adjunction has to, otherwise goes in the wrong direction. In order to make this argument wouldn't work. So this is the Schritt constant term functor for this parabolic inside G times G, and so it's given by again. Yes, well, Q mu left and right. And lower Schritt opposed with E mu in for star. At least when applied to polynomial objects, which is what we're dealing with. So the upshot is again here. Oh, let me leave that on a statement. Sorry, this is just kind of a formal. At this point, this is a formal manipulation, but I wanted to at least is that just the whole functor is a direct sum over all the mu's. The point is you don't have an adjunction without picking a mu, because some that only works if sum is the same as product. So you have that this guy, just going back to minus dual tensor, and I think I swapped. Of BunG. This is isomorphic to U times identity G. Lower shriek. U times identity of BunG. Lower shriek composed with E times identity G or star. You get by summing over all of these. And so, well, you do the same base change. And so similar base change argument. Gives that this guy applied to the U times in shriek E times G for star applied to delta lower star. Sorry, delta lower shriek of the constant sheet. Now on BunG, remember we're calculating the dual, that this is the same as that same Q times P delta on BunP of the constant sheet on BunP. Okay. So that's the calc. So so it was this kind of, so there were a few things. So let me point out a few things about this proof, and then I think I'll finish at that. And this is kind of the main input about Eisenstein series that goes into proving miraculous duality. It's pretty much formal from here on, given everything we've said. But the things that I want to emphasize about this proof is that the idea of going from these kinds of functors to kernels, and how that works, and applying this kind of second adjointness to get and playing with duality to get what the useful trick in all sorts of contexts. That's the strange functional equation, and as I said, it's essentially a formal argument from here to get the rest of miraculous duality. Stop here. Thanks.
Are there any questions?
Which paper is it?
Oh, so this is it's called a strange functional equation for Eisenstein series and miraculous duality for BunG or something like that. And strange is in quotes. Which itself is a little strange.
Yeah.
Well, let's think of speaker again.